Hi guys, welcome to 11.3, the integral test. Chapter 11, we're looking at sequences and series. We started off with sequences, which is an ordered set of numbers, and then we moved on to series, which is the sum of that infinite collection of ordered numbers. And our goal is to determine whether or not a series sums up to a finite value, or does it diverge either to infinity or just diverges by bouncing back and forth. Last class we talked about the harmonic series, and we saw that the harmonic series, the sum from n equals 1 to infinity of 1 over n, diverged to infinity. And then we looked at a group of series called the geometric series and saw that we can actually calculate the sum of a geometric series if the common ratio was between 1 and -1. Today we're going to look at another method to determine if a series is convergent or divergent. Depending on the form of the series, would depend on what test you could use. So obviously you can only use the geometric series test if it is a geometric series, but what if it's not? So today we're going to talk about the integral test. The integral test determines the convergence or the divergence of a series. If we have a function that's positive and decreasing, and we can write the function as the given sequence as the corresponding function, then the series converges only if, the corresponding integral from 1 to infinity of f of x dx converges. So, for example, let's look at, I'm going to add if and only if. All right. So, for example, we already know how this behaves. Let's look at the harmonic series, n equals 1 to infinity of 1 over n. The corresponding function is 1 over x. Now, the tricky part is determining if the hypotheses are satisfied. If f of x is continuous, positive and decreasing, this is a rational function, it's continuous on its domain, it's positive because we're only going from 1 to infinity. So if we put a positive value in the denominator fraction, it's clearly positive. Decreasing. Okay, well, we can look at the graph, but that's not using calculus to determine that this is decreasing. So what I'm going to do is just simply take the derivative, and the derivative of 1 over x is negative 1 over x squared. X squared is always positive, negative 1 is always negative, so therefore the derivative is always negative, so therefore f is decreasing. So the hypotheses are satisfied, and we also know that if we integrate from 1 to infinity, 1 over x dx is divergent. We've done this numerous times. Therefore, the harmonic series, n equals 1 to infinity of 1 over n, also diverges. There we go. All right, so the tricky part probably is showing that these conditions are satisfied. You can't just say, oh, it's obvious. So let's look at another one. Let's look at this particular series and use the integral test. Let's use the integral test to determine if this series converges or diverges. All right, so the corresponding function would be 1 over x squared plus 1. So we're looking at it only from 1 to infinity, because our series goes from 1 to infinity. F of x positive. Well, yes, that's obvious because any positive number squared plus 1 is always positive. Decreasing. Well, Well, you can look at a graph and we can definitely see that this is decreasing, but that's not sufficient. We have to use calculus to show it's decreasing, or you can use algebra. I'm going to use calculus here. I'm going to look at the derivative of this function. It would be, let's see, it would be, I'm going to think of that as x squared plus 1 to the negative 1, so it's going to be negative 1, x squared plus 1 to the negative 2, all times 2x is going to be the derivative. I'm going to clean this up, negative 2x, all over x squared plus 1 squared. For any value of x, this is positive, and the numerator is going to be negative for x greater than or equal to 1. So a negative over a positive is always going to be negative. So the derivative is negative, therefore f is decreasing. So don't forget to show that the tests for the hypotheses for the test are satisfied. So we showed that it's a positive function because 1 is positive and x squared plus 1 is always positive. To show it was decreasing, I took the derivative and showed that the derivative was always negative. So now we're going to integrate this to determine whether or not the original series is convergent or divergent. So we're going to integrate 1 to infinity, 1 over x squared plus 1 dx. So if we use our proper notation, we can't have infinite integration limits. So we're going to do 1 to t, 1 over x squared plus 1 dx. And if you remember the antiderivative, what is the antiderivative of 1 over x squared? Hopefully you remember that it's the inverse tangent of x from 1 to t. And the limit as t goes to infinity of the inverse tangent of t minus, the inverse tangent of 1. And as t goes to infinity, the inverse tangent t, how does the inverse tangent of t behave? Well, as if you remember, the tangent of t is defined between negative pi over 2 and pi over 2. So if we look at the graph of the tangent, it looks like this. And as t goes to infinity, the inverse tangent is going to approach pi over 2. So that's pi over 2. And the inverse tangent of 1, well, what angle has tangent of 1? Pi over 4. So we have pi over 2 minus pi over 4, which is pi over 4. So therefore, this integral is convergent. Thus, the corresponding series, 1 over n squared plus 1, n equals 1 to infinity, also converges. Right, now all we can determine is that this series converges. We don't know the value for which it converges. The integral has a value, it's pi over 4, but the corresponding series does not necessarily take on that same value. All we can determine and conclude is that 1 over n squared plus 1 from 1 to infinity. If we add this up, this would equal at 1, would be at 1/2. If we did 2, it would be at 1/5. If we did 3, it would be at 1/10. At 4, it would be at 1/17. And if we add this up, it would actually be less than infinity. It'd be some finite value. That's all we can determine. All right, let's try another one. What about the series? N equals 2 to infinity. All right, I threw this in here for a reason. First of all, n can't be 1. We can't start at 1 here because we'd have 1 over 1 times the natural log of 1 would have 1 over 0, so we would have a problem. Series don't necessarily have to start at 1. It's just sort of standard. By eliminating one term of a series or adding a finite number of terms does not affect the convergence or divergence. We are looking to see how this behaves eventually. So it's okay that this starts at 2. So what we're going to do is look at the corresponding function, f of x equals 1 over x times the natural log of x on 2 to infinity instead. So we have to decide, is this positive? Yes, because x is always positive from 2 to infinity, and the natural log of x is positive to the right of 1. So that definitely holds. We have to determine if this is decreasing. Oh boy, well, let's take a look. Let's take a look at the derivative. The derivative is going to be, I'm going to think of this as x natural log of x to negative 1 power, and then just use the chain rule. So it's going to be negative 1 x natural log of x to the negative 2 times the derivative of what's inside. So the derivative of what's inside is the derivative of the first, which is 1 times the second, plus the first, which is x, times the derivative of that. All right, so let's take a look. This is going to be negative natural log of x plus 1 all over x natural log of x squared. Now the denominator, whatever the denominator is, which we know from 2 to infinity is positive anyway, but we're squaring it, so the denominator is always positive, and we know the natural log of x is greater than 0 past 1, because at 1 it is 0, so we know that this is positive. So because of this, we know the whole numerator is going to be negative. So therefore, f of x is decreasing, and we can integrate. So now let's integrate from 2 to infinity, 1 over x, natural log of x, dx. If this integral converges, then the original series also converges. If this integral diverges, then the series also diverges. That's what the integral test tells us. Oops, we're going to go to t goes to infinity, 2t, that's a t, 1 over x, natural log of x, dx. I'm going to have to use u substitution. I'm going to let u equal the natural log of x. du will be 1 over x dx. So all our integration techniques are going to come back to us. So continuing on with this, we're going to just be integrating 1 over u du, which is the natural log of u. So therefore, the limit as t goes to infinity to t, 1 over x, natural log of x dx is equal to the limit as t goes to infinity. This integral is just the natural log of u, but u is the natural log of x. So it's the natural log of the natural log of x from 2 to t. So dig way back in your brains, dig out your Calc 1 stuff. The natural log of the natural log of t minus the natural log of 2. All right, now here again what gets a little tricky. The natural log of t goes to infinity as t goes to infinity. So the natural log of something getting bigger and bigger, this goes to infinity. And this is just a constant. So infinity minus a constant is still infinite. So therefore, this integral from 2 to infinity, 1 over x, natural log of x dx is divergent. Thus, the corresponding sequence, 1 over n, natural log of n equals 1 to infinity, is also divergent. Boing. There you go. I see, oh, there are all sorts of noises going on in my house. All right, kids. I'll tell you, I really am not a fan of doing this in my house. All right, let's talk about P-series. Okay, a P-series is another type of series we can generalize. So the base is what's changing, the power is going to stay constant, and this P-series is going to converge if the power is greater than 1 and divergent otherwise. So we saw previously using the box. Remember I drew the box and I said, oh, let's color in a half, and then we'll color in another half of a half, a fourth, and then an eighth, and we saw that this converged. We can also now use this test. It's a p-series, and p would be right here, the power, and that remains fixed. What's changing is the base. So here,
I'm listening.
Whoops, I said Siri. My phone didn't like that. P is equal to 2. So therefore, by the p-series, we can conclude that n equals 1 to infinity, 1 over n squared is convergent. Again, we don't have a value. We're just finding that it converges. Now this is actually a p-series in disguise, because we can think of this as 3 times 1 over n to the 1/2 power. So this constant here does not have the power applied to it, so we can disregard this constant. We actually can bring it out front because it's 3 times 1, and then it's 3 times 1 over the square root of 2, then 3 times 1 over the square root of 3. So this is really just 3 times 1 over n to the 1/2. A constant times the series does not affect the convergence or divergence, so this is a p-series, and p equals 1/2. So therefore, by this rule for p-series, (3 over the square root of n equals 1 to infinity, is divergent. Yep. All right, I'll give you a little blurb on why if you're interested. So bear with me. But this is so now we can look at geometric series, we can use integrals to determine if a series converges or diverges, or if we can make it look like this, 1 over n to some power p, disregarding constants, we can pull those out front and we can determine the convergence or divergence. So let me just give you a little proof on why this works, just so you can have good Calc 2 notes. And we can use the integral test, right? So 1 over n to the p n equals 1 to infinity corresponds to the function f of x equals 1 over x to the p on 1 to infinity. So let's integrate from 1 to infinity 1 over x to the p dx. So using our proper notation, this is the limit as t goes to infinity of 1 to t, 1 over x to the p dx, which is equal to, well, 1 over x to the p, this is just a power function, so we can think of 1 over x to the p as x to the negative p. So when we integrate some x to a power, we add 1 to the power and divide by the new power. So it's going to be x to the negative p plus 1 all over negative p plus 1. We're going from 1 to t, and then let's not forget our limit out front. Limit as t goes to infinity. Now I'm just going to rearrange this because I don't like leading with my negative. This is limit as t goes to infinity. And I'm going to do 1 over 1 minus p out front times x to the 1 minus p. And this goes from 1 to t. Now this is just some tricky algebra here. Let's look at this. Limit as t goes to infinity, 1 minus p, and it's going to be t to the 1 minus p power minus 1 to the 1 minus p power. Right? So now this, we want this value to be finite. So this is just a constant. Right? This, so as t gets really big, what's going to make this not be infinite? So this is just 1. So we have to see how this behaves. So notice if this power is negative, if 1 minus p is negative, it's going to force, if 1 minus p is negative, then t to the 1 minus p is equal to 1 over t to the sum power. And that's what we want. We want 1 over t to the sum power. So then as t goes to infinity, this whole thing will go to 0. So if 1 minus p is negative, t to the 1 minus p will be in the denominator. We'll force the t in the denominator, and that will go to 0. So 1 minus p is negative when 1 is less than p, or when p is greater than 1. So, therefore, so that is this integral 1 to infinity 1 over x to the p dx diverges if p is less than 1 and converges, no, less than or equal to 1, because if it's equal to 1, then we have the integral of the natural log, so in this, and that we know diverges. So therefore, 1 over n to the p, n equals 1 to infinity, converges if p is greater than 1. All right, to do. Read 11.3 exercises 3 to 27 odd. Great practice for your integration. Don't disregard. The hypotheses. Is f of x positive? Is f of x decreasing? All right, coming up next will be the comparison test. See ya.